Welcome to part 10 of the lecture on stoichiometric organometallic synthesis. Subject of today is diastereoselectivity through chair transition states. Certainly you all know the Claisen rearrangement. Claisen rearrangement as an oxacope rearrangement has that oxygen involved, an enol and allyl ether, and at elevated temperatures, usually above 100 degrees, and there are numerous examples. We have to heat it up, especially if part of that is an aromatic system. You have to heat it up to about 180 degrees. Resulting in a gamma delta unsaturated carbonyl compound. And as you see, these positions with the R and the R prime group have now formed chiral centers. And it's interesting to figure out what kind of diastereoselectivity should be predicted for such reactions. Well, the Claisen rearrangement is not an organometallic reaction, but there is a reaction connected with the Claisen rearrangement. If you have an OR group there, then you are dealing with ester enolates. And the reaction, the rearrangement reaction of these ester enolates is called the Ireland reaction. Or Ireland-Claisen rearrangement, which has been developed in the 1970s. So, well, you start with an allyl ester. Usually you deprotonate with LDA, and now we are within organometallic chemistry. You deprotonate with LDA, THF at minus 78 degrees, and you trap usually the enolate with trimethylsilyl chloride, thus obtaining a stabilized ester TMS enolate. If you heat it up above 70 degrees, the rearrangement occurs. Giving rise to this final product. Well, the derivative in this case, well, it's TMS ester of, again, an gamma delta unsaturated carboxylic acid. This reaction also works directly with the lithium enolate However, heating up a strongly basic lithium enolate, well, you can be sure that you have a couple of competing reactions then, and the TMS enolate usually leads to cleaner products for the Ireland rearrangement. So, the transition state you can draw like this with dotted lines here. Essentially, it's the same like that. And well, 6 electrons are involved. And this is called then a 6-membered aromatic transition state. Although the transition state is not planar, and this becomes important for explaining the diastereoselectivity of a reaction. So let's clarify the 3-dimensional structure of a transition state. For the Ireland-Claisen rearrangement to occur, the acyclic starting material needs to adopt a certain conformation. A conformation which then can lead to a chair-like 6-membered transition state. So this is the 3-dimensional structure. And this should be the final outcome. Well, now we have to look for what happens if we have some additional substituents that we therefore generate chiral centers. Okay, therefore, we should have a look at the most simple example, the one having 2 additional methyl groups in these positions. With LDA in THF, well, it's always the same, the minus 78 degrees. Secondly, TMSCl. We then get the TMS enol ether. And now what is important, this enol ether has trans selectivity. It is the trans enolate, or you can also call it the E-enolate. adopting this conformation, the necessary conformation, means we have to assume this conformer or the conformer that is essentially the mirror image of this one. So this conformer, of course, is chiral, and if we put on a star here, we just mark that we have this or the mirror image. This transformation through that 6-membered transition state then leads to the product CH3 group and CH3 group. And if we analyze this structure according to Kahn-Ingold-Prelog, then we notice that we have drawn here the 2s, 3s diastereoisomer, and since we could have this one of a mirror image, and we didn't put any chiral information in there, we shouldn't get chiral information out of it. Yeah? Well, we just put on the stars here, and this tells us that we have equal amounts of the two enantiomers, the 2s, 3s, and the 3s, no, the 3, sorry, the 2s, it's the 2s, 3s plus the 2r, 3r, enantiomer in equal amounts, of course. It's a racemic mixture, simply. Well, the ratio of this diastereoisomer to the other one is 9:1. If we slightly change the reaction conditions, the same, almost the same as that, but adding HMPA. Hexamethylphosphoric acid amide. Now the solvent that is highly toxic, on the other hand, is important for complexating, for instance, lithium cations. Then the result is much different. We then have preferentially the Z-enolate again adopting the conformer, which then can proceed forward the rearrangement reaction. And again, analyzing that tells us we have a 2R star, 3S star diastereoisomer with a selectivity of 4 to 1. Nice result. However, we should now think about the explanation. Why do we get these selectivities? Preferentially E-enolate under simple reaction conditions, and preferentially the Z-enolate with the addition of HMPA. So, we have to think about the mechanism of the enolate formation. Let's abbreviate the starting material as this. For Ireland-Claisen, you have, of course, the R group is an alkoxy group. Yes, it's of course then an ester, but it essentially works the same with, well, for instance, ketones. So, and we have as the base aldeA. The deprotonation again occurs with a 6-membered transition state. This is the usual tag, the double cross for transition state. So the question is about the selectivity, cis-trans selectivity here for that, in this case, methyl group. Again, you may have noticed we have a 6-membered transition state with overall 6 electrons involved. And indeed, the same as before, an aromatic transition state with a chair-like conformation is also involved in this case, and this will indeed explain the selectivity we have observed. So let's try to draw that . So, the lithium amide coordinates to the carbonyl group. And here we have a free electron pair at the nitrogen, and this then deprotonates the acidic alpha position. And well, you here notice that we have again a chair-like system. However, if we now rotate around this carbon-carbon bond, well, which situation do we have then? CH3 group is here on this side, there is the hydrogen, and here the other one. Then we have this situation. Oh, sorry. We have isopropyl groups here, not tertiary butyl groups. Nevertheless, also with the isopropyl groups, they are bulky enough that in this case we have clearly a steric repulsion between the CH3 group and this isopropyl group, both adopting axial positions in this coordinated chair, and therefore we have an sterical repulsion between a 1,3 diaxial steric repulsion. And that means, because the CH3 group is of course bigger than the hydrogen here the steric repulsion is lower than there, and we should assume that we have an equilibrium between those two structures, and this is the favored one. So, the favored one results in the E-enolate just as we have it observed in the experiments. Well, not we, but others. Okay. A deprotonation of this kind would, of course, give us the Z-enolate. Now, what about adding the HMPT? Let's draw that again. The nitrogen with a free electron pair will deprotonate the acidic hydrogen here. But now the lithium does not coordinate to the carbonyl oxygen, since the lithium is already occupied by the solvent. The HMPA is coordinating to the lithium. And now this situation is disfavored since we have the steric repulsion between the CH3 group and that substituent R. So now the selectivity in the equilibrium should be the opposite. This is the favored situation with the smaller hydrogen, smaller than the CH3 group, close to the substituent R. And the other stuff we have to draw is all the same. And now we have preferentially, of course, the Z enolate. Actually, if you change to an even more sterically hindered base and leave off the HMPA, then you get the E-enolate with up to 70 to 1 selectivity. Well, under optimized reaction conditions with some other reagents, lithium bromide and some other tricks what people do to optimize. So, what do we achieve with an Ireland-Claisen reaction? We start from an allylic alcohol performing esterification, simple reaction, and the rearrangement of the E-enolate delivers final product with high selectivity and this diastereo isomer here S star and there also the S star. Well, this is the erythro isomer. You might know this stereochemical descriptor. The other one would be the trio isomer. So, the trio isomer you could approach with the HMPA trick, let's call it like that. Or if you want to avoid the HMPA, and that makes sense as we have already discussed before, yeah? Or better, just start with the cis olefin, the isomeric cis olefin. This one. The Ireland-Claisen rearrangement is a very powerful method for synthesis. Achievements. also to summarize. A, we have in the product two stereogenic centers. Whereas in starting material we have none. Well, except this trans isomer of the olefinic moiety. B, we are targeting selectively for the diastereoisomers by this process we are investing a CO bond and getting, in exchange for that, a CC bond, which is within a C5 chain. And usually, as you know, CO bonds are very easily synthesized, nucleophilic substitution or esterification and so on, where it's harder to get CC bonds. No? Well, moreover, D, we have two versatile terminal functional groups. Can perform all the reactions acids are known for, esterification, or we can reduce it, having there then an alcohol. On the other hand, with the olefin, we could perform addition reactions. We could, for instance, make an ozonolysis, having access then to an aldehyde, and so on. Well, for making use of the Ireland-Claisen rearrangements in planning organic synthesis or designing organic synthesis, you might remember the retron concept could be a good idea. Well, the retron of an Ireland-Claisen rearrangement is that gamma delta unsaturated carboxylic acid. This is the retron. So, if you have in your target molecule such a moiety, maybe with some other substituent here, no problem, yeah? Which tells you you should think about applying an Ireland-Claisen rearrangement for synthesizing this target. So, usually you analyze your target following the ideas of retrosynthesis, and this retron tells you should look for something like that as the starting material, and doing that retrosynthetic analysis. Then, for these more complicated retrons, it is a good idea to put on some numbers. So let's have a look for a target as an exercise. This is the target, and please think about what could be the starting material for this target molecule making use of an Ireland-Claisen rearrangement. So some of you noticed that it's better to put the tag 1 to this oxygen. So, and well, let's count. Here we have that gamma delta unsaturated acid. So, the oxygen 1, carbon 2, this is 3, this is 4, this is 5, this is 6. Okay. Following the retrosynthetic arrow, we have to connect the oxygen 1 with a position 6. So that means this is essentially following the numbers while drawing. In German you call that Malen nach Zahlen. So nothing is changed with the stereogenic center. At the 6th position, we have the oxygen there. Then the double bond migrates from the position between 5 and 6 to the position between 4 and 5. That's of course here. Well, okay, and let's add the acetyl group here. It's clear that as we have then that side chain in the resulting reaction, so Ireland-Claisen or Ireland reaction, we have this substituent on the same side as that here. And during Ireland-Claisen reaction, this group has to stay on this side. It wouldn't tunnel to the other side. The stereochemistry that is involved is clear. We have to have both substituents on the same side of a ring. And this will automatically lead to this stereo information, to this configuration here. Let us assume that we have an additional methyl group here. Then we have to add a methyl group there, forming the enolate and then having that rearrangement. For this it is rather difficult, a bit more tricky to predict the stereochemical outcome. Of course, we could just do it like we have done before in these examples. However, the examples are for acyclic systems. Now we have a transition state, a 6-member transition state with an annihilated 5-membered ring. This introduces some constraints, and therefore it could be possible that in this case the transition state, the preferred transition state is not a chair-like but a boat-like transition state. Couldn't know by simple consideration. However, well, one could have a closer look, having some calculations, or just make the experiment if under simple reaction conditions, having started with the E-enolate, you have the wrong stereochemical outcome, well, then change the reaction conditions to the Z-enolate. Next exercise. An interesting starting material. We have changed from the terminal methyl group to a hydroxyl group. Reaction conditions LDA, THF, TMSCl, all in excess. Then doing the Ireland-Claisen rearrangement. Please make a prediction what will be the product you would anticipate. So, especially concerning the stereo information. So, what will happen? The hydroxyl hydrogen is the most acidic one, therefore this is deprotonated first, and then immediately trapped by TMSCl if TMSCl is already present. So, first step, having LDA and TMSCl in excess means that you can now deprotonate a second time, forming the enolate and then trapping again. So, under reaction conditions, you have learned that they are usually significant for the formation of the E-enolate. Therefore, it is an educated guess that we will have this intermediate product, heating it up to a temperature where the rearrangement occurs. This should then give, after hydrolysis, the erythro diastereoisomer. Since we've started with the E-enolate and the trans olefin. If you really perform that reaction, the end, you will notice, well, something is wrong in that prediction, because you get mainly the trio product in this case. Now, what could be wrong with the prediction? Through all steps we followed what we have learned before. Anyone with an idea? Well, here it's, yes? Okay, this is a steric argument. Yeah? Well, it's not the main argument. Last lesson we talked about Cram's rule and Felkin-Ahn model. And then we had an example where everything was turned around by a chelate effect. Also in this case, a chelate effect turns the selectivity around. So actually, the trio product preferred with 39 to 1. A chelate effect is responsible for that, and this is simply explained the lithium enolate is stabilized by this oxygen if we have a cis isomer. Well, and therefore then the cis isomer is trapped as the TMS enolate and finally leads to the trio product. Okay, enough for today. Thank you for listening. Next week a related subject. We have to discuss a related subject, aldol addition processes, which also proceed through six-membered transition states. Again, thank you for listening. See you next week.